acceleration is, I gave you a whole bunch of room on this page, and I'm going to apologize because example 6, you won't have enough. So you might need to leave a little space on this page for the next page. So just FYI. Okay, so the first thing I'm going to really star is this. Acceleration is the rate of change of velocity. And this is all just a step up from when we talked about velocity. If average velocity is the slope of 2 position points, average acceleration is just the slope of 2 velocity points. So everything we did from displacement to velocity, we're now just doing from velocity to acceleration. So this is literally SVA. I just do it vertically, they do it horizontally. The derivative of position is velocity, derivative of velocity is acceleration, antiderivative of acceleration is velocity, antiderivative of velocity is position. So this is all stuff that we know. And maybe that too. The other thing, units of acceleration, meters per second squared. So it's just getting your time to the second power. All right, so the examples are quite in depth and lengthy, so let's look at that first. A particle moves in a straight line with relative position relative to the origin, given this equation. Time is just greater than or equal to 0, which makes sense. So this just wants expressions for velocity and acceleration and sign diagrams for each. So let me just move this up. Now we'll do it this way. So S V derivative, remember we're on derivatives, 3t squared A derivative SVA. Okay, now we just need, in order to do the sign diagrams, the very first thing you want to do, set them both equal to 0. So for velocity, here, I'm going to move this up a little bit. So first I'm going to factor my 3 out of my velocity function. It will make factoring it much easier. Factors of 3, then add to get -4. So time 3 and time 1, the velocity is 0, so it changes direction. So I'm going to start at 0, and it's just going to go, we don't have an ending, so let's just label that velocity. And then I'm going to put in 1 and 3. Okay. So if I pick a value between 0 and 1, I'll look at a half. I plug a half in for each of my t's. This is always positive, and this will be negative, and that'll be negative. So a negative times a negative, this region is positive. Then I'm going to look at 2, positive, plug in 2, this would be negative, this would be positive. So the whole region is negative. And anything greater than 3 makes the entire thing positive. So it'll be positive. All right, then I need to make my acceleration 0 and solve for t. So I'm going to add 12 to both sides, divide by 6. So the only time this changes acceleration is at time 2. So start at 0, 2, and always label everything. So this is going to be for acceleration. If I plug in 1 for t, 6 times 1 minus 12, that'll be negative. Anything greater than 2, like 3, that's going to be a positive. So that's everything for letter A. Okay, find the initial conditions and describe the motion. So Initial conditions, we're just going to use all of this and plug in 0. So S of 0, if I plug 0 in for everything, I get -1. V of 0, plug in 0, you get 9. And A of 0 is -12. Okay. So if we want to describe the motion, so this is in relationship to the origin. So the particle begins one centimeter left of the origin and is moving to the right at a velocity of 9 centimeters per second and an acceleration of -12 centimeters per second squared. Okay. All right, let's look at letter C. We're going to go back to what we got here because the velocity sign diagram tells us when it changes direction at time 1 and 3. So this was B. C, we want to find our S of 1, so just plug 1 back in for S. 1 minus 6 plus 9 minus 1 is 3. And then we plug 3 in. You plug 3 in for all your T's for here, you get -1. So that's the shortest part of this one, right? Okay, then letter D, we're just going to create a motion diagram for everything we just figured out. Okay, so we always start our motion diagram with our position and always in relative to the origin. So let's remember we started out 1 to the left of the origin, and at some point we get to 3, and it's good to label. Okay, so I begin at time 0, I'm at -1. So I'm going to label time 0, begin at -1, moving to the right, and I move to the right until I get to time 3. Nope. Sorry, this way. Time 1 here. Time 1, I had that. At time 1, see that you gotta be really careful. This is your position. So I'm gonna go to this position and label it time 1. Then I'm gonna come back until I get to -1. This is time 3. And then I turn back around. So this point is time 3. So I start with my initial position at time 0 is at -1, moving to the right, and at time 1, I am at position 3, turning left, and time 3, I turn back around and go right for the rest of the trip. All right. Now, find the total distance traveled. So we can just count this. We actually can see everything on this motion diagram. So I started here. How far did I go in the first 3 seconds? Okay, So from here to here, this is the first 1 second. I went 1, 2, 3, 4. Then I turned around and went 5, 6, 7, 8. First 3 seconds. So I'm going to say 4 plus 4 is 8 centimeters. So be really careful you're paying attention to time. This is at where I'm at 3. So I have to count all of my steps until I get to 3 seconds. So that is example 5. All right, example 6 is where you really run out of room because I needed all of the space for A and B, and then I really didn't have much room for C. Okay, so let's begin. Let me move this up a little bit. So A of T is 1/2 e to the negative t over 100. Be really careful how you write that. This should all be in the exponent. So how do I find velocity if I'm going from acceleration to velocity? So think SVA, we're going backwards. So we need to do the antiderivative. So the nice thing about E is it's just E. So I'm going to bring everything down. Here's where people forget. You must counteract the exponent. And because it's antiderivative, we have to divide out the exponent. So the derivative of the exponent is negative 1 over 100. If I divide by negative 1 over 100, I multiply by negative 100 over 1. So the whole fraction thing, be very careful. And don't forget your plus C. So then I can simplify negative 100 over 2. My velocity function is negative 50 e to the negative t over 100 plus c. Okay. One thing I got to show you up here. It says a train is initially at rest. At rest means v of 0. At time 0, it's at rest is 0. So this right here allows me to find my c. So v of 0 is just 0. And this whole thing is 0. Anything to the 0 power is 1 times 50 is negative 50 here. Add it to the other side. My constant is 50. So my complete function for my velocity, this is my finished velocity function. All right, I'm not going to sketch this because you really won't have room. Finding it is the big thing. Okay, how long, that's time, will it take for this train to reach a speed, which is velocity, of 40? So for letter B, I'm literally just finding when the velocity, this function here, is 40. So now I'm just going to solve this for t. So our first step, subtract 50 from both sides. Divide by negative 50. And it'll be easier if we just reduce this and leave it as a fraction. Now, if I'm solving for t, I need to counteract ln with, I need to counteract e with its inverse, which is ln. So that cancels that out. And I'm going to tell you it's going to be easier to move that 5 up and take ln 5 to the negative 1. Now, you'll see why in a second here. Then I'm going to bring down my negative t over 100. Now here's some of your logarithm rules. Any exponent with a log you can bring down front. Negative ln 5. So if I multiply both sides by a -1, it makes everything positive. Then I just multiply by 100. So t, the time it takes, is 100 ln 5. So that's your b. And that is going to be seconds. Now, what's kind of awkward for people, you could always, always, always leave things in terms of ln and e. It's just going to be easier later when we're solving. All right, this is the part that I'm going to apologize for. Now we have an even longer problem for part C. How far will it travel in this time? So this is the time it's talking about. How far it's going to travel is distance. And if we have a velocity function, how do we get from velocity to position? We're going to go backwards one more time. So for part C, we are going to integrate from our starting point of 0 to our time of 100 ln 5. We're going to integrate our velocity function. So when I integrate -50 e to the -t over 100, this is kind of yucky, but we just bring down the -50 e to the -t over 100, dividing out the exponent. So that's -1 over 100 or -100 over 1. If you divide by -1 over 100, multiply by the reciprocal, plus 50 gets the t. Oh, and I don't need the c because I'm going to evaluate from 0 to my 100 ln 5. All right, so let's simplify this. This is just -100 times -50. That's 5,000. All of that plus 50t from 0 to all that. All right, let me make some more room. All right, so this is kind of ugly. So first thing I'm going to do is plug in this. So I'm just going to show you everything. So -100 ln 5 divided by 100 plus 50 times 100 ln 5. That's this whole thing minus plug in 0. When I plug 0 in for my exponent here, e to the 0 is just 1. So this is just 5,000, and this is just 0. So that's that whole thing. Okay. So here the hundreds cancel, so that kind of turns out nice. Then this negative, I can't see how that negative is in between e and ln. I got to move them. So I'm going to move this back to being an exponent. So bring down the 5,000, then this cancels, and I'm left with 5 to the -1, which is our 1/5, plus 50 times 100, that's 5,000 ln 5, minus 5,000. All right, this turns into 1,000. And then I can combine my 1,000 minus 5,000 to get -4,000, bringing down 5,000 ln 5. And to me, you can leave it like this. If you were to plug this into your calculator, and I think this is in meters, this would be this simplified. But you're always okay leaving it as exact. In fact, to me, it would be better, but they might ask for it. That is section C.